In some applications, we may need our model to track multiple variables that depend on a single independent variable. We have discussed population models for species mostly one at a time, but we could have two species whose populations change over time and are impacted by each other. The most common application of this is called the predator-prey model, where one species relies on the other for food. Consider the population of rabbits and foxes, where the foxes eat the rabbits. And x of t and y of t are defined as the number of rabbits and the number of foxes, respectively. So x of t is the number of rabbits, and y of t is the number of foxes. Then for positive values a, c, alpha, and gamma, we can represent this with the two differential equations dx dt equals ax minus alpha times xy, and dy dt is negative cx plus gamma times xy. In this model, the fox population benefits from fox-rabbit interactions, that xy term, with a positive constant gamma in its differential equation. dy dt is negative cx plus gamma times xy. Conversely, the rabbit population is negatively impacted by these interactions since they get eaten. So there is a negative constant, negative alpha, of the interactions of the differential equation for x. While we can't solve these two differential equations directly, we could plot a direction field or slope field by finding dx dt and dy dt at several points, then computing dy dx as dy dt over dx dt to plot the direction field in the xy plane. Doing this, we can sketch in some solutions. What we'll find is that for a low population of foxes, the number of rabbits will increase. After this happens, the number of foxes will increase since there's plenty of food. But as the number of foxes increases, the number of rabbits dramatically decreases. And with less rabbits, there will be less to eat, so there will be less foxes, giving way to this periodic solution. A model like this is called the system of differential equations, because we have more than one differential equation, here dx dt and dy dt, that rely on both xy and the independent variable t. In general, if we have a set of n functions, x1 up to xn, a system of differential equations for the xi's is given by x1 prime is a function of t and all of the x's, x2 prime is another function f2 of t and all of the x's, all the way down the line for every function x, down to xn prime is some function fn of t, x1, x2, and all of the x's up to xn. Notice that each derivative xi prime depends on the independent variable t as well as the other dependent variables xj for j between 1 and n. And that is why we write each xi prime as a function of t, x1, x2, all the way up to xn. Now up until this point, we have been studying single differential equations. And similar to a solution of a single differential equation being a function that made the differential equation true, a solution to a system of differential equations is a set of functions, x1 equals phi1, x2 equals phi2, all the way up to xn equals phi n, that make all of the differential equations true simultaneously. And an initial value problem is a system of differential equations like above, together with initial conditions for each xi at some value t equals t naught. Please recall that when we were studying differential equations, we had a theorem about uniqueness and existence of solutions. The existence part told us that our differential equations would have a solution, while the uniqueness told us that if we were to find a solution, it would be the only one. We have a similar existence and uniqueness theorem for systems of differential equations. For a set of n functions, f1 up to fn, and their n squared partial derivatives, partial of f1 with respect to x1, all the way up to partial of f1 with respect to fn, for every function f, all the way up to the partial of fn with respect to x1 through the partial of fn with respect to xn, that are continuous on a region R, then there is a t interval, t between t0 minus h to t0 plus h, where there exists a unique solution to a system of differential equations with initial conditions given at t equals t0. So similar to our single differential equations, our systems of differential equations will have unique solutions so long as the functions are nice enough.